For determining the period of a planet, that is the time it needs to orbit the Sun, we just need to observe a fraction of the planet's orbit. So here we're looking at Neptune on April 26, 2008, and I'm going to go in increments of 14 days, and I'm going to take a snapshot of this particular one here, the first one, and I'm going to go in increments of 14 days, and we see that Neptune orbits first towards the east, and then it retrogrades. I guess that's kind of point I caught it in its orbit, and it stops retrograding. You can follow the time in the upper left. And so here we're in 2009. There's actually Jupiter arriving, and I'm going to go manually 1 day forward, and I'm going to take another snapshot of this picture, and then I'm going to measure the two snapshots. So I adjusted the ruler here in a graphing software so that would fit the coordinates here. So Neptune, April 26, 2008, looks like 6 here, so 36 degrees, and then exactly a year later it looks like 3.8, so 33.8 degrees. So when I plug in these two numbers, so 36 minus 33.8 is 2.2 degrees in 1 year. Since I know that there are 360 degrees in a circle, I divide 360 by 2.2, and that means that Neptune would take 163.6 years to orbit the Sun. This compares very nicely to the accepted value of 164.7 years. One little caveat here, I would have to pay attention to that I don't catch it during a very elliptical part of its orbit. But for the most part, the planet's orbits are relatively circular, so that's why my result comes out pretty close to the way it's supposed to be. So in order to determine the distance to Neptune, what I need to do is look at its parallax during retrograde motion, capture the frames when it starts retrograde motion and when it ends, and analyze those. So here we go. And there it goes into retrograde, which was May 26th. I also confirmed that in an almanac. And here it stops again. That's November 7th. And so those two frames I record. So here's May 26th when it starts retrograde motion, and it's right there, and that looks like 35.75 degrees. Then I'm looking at, by the way, the moon was also close to Neptune on that day. And then here, November 7th, it's really on the far right there, and I'm measuring 38.5 degrees, and those two I'm going to analyze. This particular Excel sheet here will actually be used in a lab where all you have to do is plug in the numbers that we just measured, and I'm going to do so for Neptune. I said here 26th of May to 7th of November, and I'm calculating that's a total of 165 days. So I'm going to plug that in, 165 days. I already know the period for Neptune, 164 years. That's just a coincidence that these two numbers are so close to each other. Remember, this one is in years, that's its period, this is the number of days. That's retrograde. And here are the two angles that I measured, and I subtract them, come up to 2.75. And I plug in these numbers, and then I'm going to shift over here and see what I come up with a distance of 30.45 astronomical units to the Sun. That compares really nicely to the true distance to the Sun of 30 astronomical units. And using all this trigonometry, which is hidden in this Excel sheet, so you don't have to do that. The Excel sheet is going to do it for you. we are able to determine the distance. The only way to determine Neptune's mass would be using Kepler's third law, and we need an object to orbit Neptune, and that would be its largest moon, Triton. Could be anything else, but I chose Triton. So we're going to watch Triton as it orbits Neptune and measure how long it takes and at what distance it is. So starting June 24th at 23 hours, we have Triton orbiting Neptune. And a little bit more right there. Okay, so here we have June 30th, 20 hours, so that's 5 days and 21 hours, which is 141 hours. I'm going to write that down. Now we need the distance from Triton to Neptune, so we would have to determine the angular distance between the two here, and then trigonometrically multiply with the distance from us to Neptune. And I did that on the side, and I came up with around 280,000 kilometers. And when we click on Triton here and pull up the information right there, then we can see that my 283,000 kilometers is quite a bit off from the true 355,000 kilometers. Well, the reason is that Triton's orbit is not face on as we may envision it, but lies at an angle of 158 degrees. If it was lying at a 90-degree angle, we would have face on. Here we would have to do some more subtle observations and calculations in order to come up with what is called the inclination of its orbit, and then we could determine its distance correctly to 355,000 kilometers. Since I don't want to go so far here, I'm just going to use the 355,000 kilometers. Also notice here that it says 141 hours. Well, that's what I just came up for the period. So I'm going to plug in these numbers into a calculator. So according to Newton's form of Kepler's third law, this would be 4 pi squared divided by the gravitational constant multiply by the distance, 355,000 kilometers, which has to be converted to meters, so another 3 zeros, because it has to be base units, and that needs to be to the third power. Divide by the period, but not by 141 hours, but by 507,600 seconds, because again it has to be base units, squared. Again, Kepler's third law. Hit enter, and we come up with 1.02 10 to the 26 kilograms is the mass of Neptune. And when you compare that to what's listed, for example, on Wikipedia, then you can see that is right on. We can also divide this by the mass of Earth, which is 5.97 10 to the 24th. And that means that Neptune is roughly 17 times more massive than Earth, and we can see that in our textbook it's also listed there as 17 times. So again, in order to determine the mass of Neptune, we need to observe one of its moons in orbit, measure the distance, measure the time it takes to orbit, and use Newton's form of Kepler's third law.